I'm Levin, and I'm from Yandex. But actually, Yandex is the #1 search engine in Russia, with around like 60% of search share, with Google having around 33%. And I work as a data scientist for Yandex Data Factory, which is like a small internal startup inside Yandex, and I'll tell you a few words about that. So it was created in 2014. And the idea is that Yandex has been using machine learning heavily for different services inside, starting from search and ad split prediction, and also working with recommendations, traffic jams predictions, and many other services. And we wanted to apply some of our assets, like our strengths in machine learning, in computing resources, in the infrastructure built for machine learning experiments, both offline and online, and our data scientists, for which we actually have a school called Yandex School of Data Analysis, which accepts 200 students each year from Russia and a few neighboring countries, from the top technical universities, and we basically graduate 100 data scientists each year after a 2-year master's program, which is free, unfortunately in Russia currently, but we get really good influx of data scientists because of this program, which already exists for 8 years. So we wanted to apply all that to basically help other companies solve their machine learning problems. And we already made very different projects in banking, in telecoms, helping federal road agencies in the airspace and just space programs companies, and many different areas. And most of the times we used our tool called MatrixNet, which is both used inside and now was used many times outside successfully in applications of machine learning to real-world problems. So what is that? So basically, it is our proprietary implementation of algorithm called gradient boosting over decision trees, but of course with a lot of details there. So I suppose most of you know what gradient boosting is, at least heard and most probably used, because rare Kaggle competition comes today without a winner using XGBoost or something like that. But just a quick reminder of what that is. So basically, when we have a machine learning problem, most often we can present it as a problem of function optimization, where we want to minimize the error, and the error is represented with a cost function. We want to optimize the function, we can do that with a gradient descent. That is where the gradient is from. Where boosting is from the boosting framework, when you learn a few weak learners, and then each next weak learner depends on the combination of the previous learners that you already learned in some way to improve the ensemble. So the question is how to combine those two, and here is the genius idea, which most of people usually don't know or don't remember, is that the gradient descent is not over weights of those classifiers and not over weights of objects, it is actually over target. So basically we represent our cost function as a function of predictions on our object, and each next classifier trains to be as close to the vector of anti-gradient as a function of objects in the space of predictions. So, and then we try to approximate our gradient vector of size m, where m is the size of data set, with a decision tree, for example. So this is the general idea of gradient boosting, and decision trees is just an example of what can be used as a weak learner, but most of the time this is what is actually used in practice. So what we have in MatrixNet is different regimes, for example, for classification, for regression, for ranking, and I'll give you examples of applications of those in practice, and of course there are much more objectives than that actually. So the main features for the users is the following. First, it was initially developed in a kind of meta-learning fashion, when we took many data sets from inside Yandex, outside Yandex, and tried to to use those heuristics on top of the general algorithm that uniformly improve the results on a huge set of data sets, so that the algorithm basically works well without too much parameter tuning, so that we don't spend time on that. That is really easy to use to the point of managers, not only software engineers or data scientists, being able to use it at least for the problem, maybe not with the best results, but at least with some reasonable results to test their product hypothesis. Of course, it's highly optimized in the first priority for application, because we get like tens of thousands, hundreds of thousands of requests per second for some of the services, and inside each request we need to score with MatrixNet like thousands of ads or tens of thousands of search results, and that's why I need to do that really fast. But also it is optimized for training, because we do like thousands of experiments a year in production and many more offline, and you need to speed up the experiments basically if you want to move fast. The training can be both local, if you want to debug something or do something really quick on a small data set, or it can be parallelized on a big cluster of machines to really train a huge data set and do that faster. So there are many applications at Yandex, starting with, of course, web search ranking, which was the reason for creating that. Also, ads quick prediction, which is a very important problem for increasing the revenue of the company. Also for external projects of Yandex Data Factory, and these three I will give you some detailed examples later in the talk. Also use it actually for recommendations. So what is, for example, today is a mainstream recommendation is either some kind of SVD approach or some kind of neural networks approach, but that is mostly about this huge matrix, users and movies, and predicting the entries of the metrics, just given some entries which are already known. But what if you need to incorporate different features there, like context features? And what if you want to also incorporate statistics or some implicit feedback or some explicit feedback? So what you can actually do is use both SVD or both neural networks and statistical features, context features, and put that inside a huge model for MatrixNet and do, for example, a classification problem to predict probability that this user will like this item or something like that. So that really improves everything and improves quality a lot, and that is a scalable approach, because you just add features if you had an idea, and machine learning just scales with the number of features. Also use it for bot detection. That's clear how to do that. Another interesting case is NLP, resolving homonymy, where you can actually profit from posing this problem in a different way. Of course, you can do that as a binary classification. This is about when you have a word which is written the same way, but has a different meaning, like a table, this one, and a table in a database. And depending on the context, you need to predict which meaning was used. So of course, you can pose this as a binary classification or a multi-classification problem, but it turns out that you can actually improve things a lot if instead of multi-classification, pose it as a ranking problem. When you have different strength to which this meaning is close to the correct meaning, like the form. The semantics can be very different, and you have like 5 variants of the meaning of the same word, and some of them are more correct than others. And if you pose this problem as a ranking problem and change the objective function of your classifier, which is easy to do with MatrixNet, and your quality can go up as much as like 15% just from that change. So that is a huge improvement that you can play with different cost functions. Also use it for user segmentation tasks like lookalikes and many other problems. So some of the tricks used inside and features it provides. The first distinguishing thing is that we actually use oblivious trees inside. What does it mean is that a regular decision forest or gradient boosting or decision trees, you use just arbitrary decision trees, which go like that. You split by one feature, and then depending on that feature, you go right or left, and then in this node to the right and this node to the left are independent. You can split differently on each level different nodes. And oblivious trees are much simpler than that, so that for each level you only split by the same condition, which in our case is both a matter of optimization, which obviously works faster, and a matter of regularization, which turned out to work much better in practice. So you just don't build arbitrary trees, you build regularized trees, which are also much faster to evaluate. Another very important thing is that you should do some regularization of your predictions and beliefs. So what people usually do is like you make some restriction on how many objects can be in your leaf, and you just don't split if there are too few objects in some of the splits. But we cannot do that with oblivious trees from one point. And from another point, we just found that another thing works better when you split up to the predefined number of levels, and then depending on the number of objects in the leaf, you can apply a discount function which depends on this number, and then just discount those leaves where you have very few objects. And then if you play with different heuristics for this function, you can get really good ones which work on different data sets as well. Another regularization thing which protects from overfitting is that we gradually increase model complexity. So you basically need to first start with very, very simple trees with like one or two features used only, and then when you get all the strength you can from such simple trees, you can increase your tree depth and try to fit in more precision into that. This also, I mean, this schedule of increasing model complexity of course matters, and you have to play a lot with these parameters to get it working, but once it's done by some meta learning, you don't need to do that anymore in the practical applications, which is good. So some of the features provides different objectives, already talked about that, so of course mean square error, log loss, but also some non-standard measures, cost functions for ranking, for example, and combinations, which can be really useful, and I'll show you an example. Also, feature generalization is one of the regularizations used. So feature generalization is done beforehand, which is like somewhat non-conventional, but it also works as a kind of regularization. So you do just binarization of a feature once, and you use that binarization in the whole algorithm. And of course, you can try a lot of different heuristics for feature binarization. We tried many, selected those which work best for our dataset. And one of the other features in the AND, it estimates feature importance and correlation, which is very important for such complex algorithms. Because basically, as a data scientist, when you train such complex models like gradient boosting with thousands or hundreds of thousands of trees, you can't understand what happens inside. Even if business asks you why did it do such prediction, this is a trade-off. This is much more precise, but then simple models much less transparent. However, you can make it really much more transparent if you, for example, compute the top features which contribute to your predictions, and you can do that in several ways. One of the ways is you take a feature and you see how much did it actually change the value of your prediction on average. You of course do that on a tree-by-tree basis and then aggregate somehow. And so really strong features tend to influence the score a lot. But what happens a lot in web search when you have like thousands of features, you really don't want to miss a good feature. And a good feature can be really sparse in the terms that it is rarely non-zero, for example, but when it is non-zero, it is very powerful. So what you want to measure is also some efficiency, which we call inside, is how much does it influence the score when it is actually different from the default values, something like that. And you can think of many different variants of how to implement that. The main thing is that you should, because if you don't do that, you can miss 100 very not very strong features on the global level, which are very strong on the local level, and then you've lost a lot of precision because you just throw them all out. out on the testing phase. So some of the applications. So for ranking, how it can be applied. So this is web search ranking. Of course, we train on judged pairs of queries and documents. Also should include probably geographic region, but that is details. Typically, people have like 5 levels of judgments, from excellent to bad and stupid. And you generate lots and lots of features per query, per document, per the pair of query and document, like PM25, and many other things, click-based, URL-based, and host authority-based, and many others. And then you can actually set this problem different ways. So one of the ways, you set it as a multi-classification problem into 5 classes, and your objective is cross-entropy. You have such objective function in MatrixNet, you train it. Another way is you do regression, and that is better because when you do multi-classification, you don't use the fact that the labels are somewhat ranked, and with regression you do use this. And your objective is mean square error, for example, but you can do even better because if you do just regression, you actually don't need to compare the score of first document for first query with the score of second document for second query. That comparison is meaningless. So, and when you're trying to predict the exact labels as numbers, like x1 plus 1 and 2 is 0.8, your algorithm spends, weights basically some of its power to make those also comparable, which you don't need. You only need to rank documents inside the search query, and to do that, you can use some ranking objective. For example, NDCG. That is unfortunately not smooth, so no gradient for gradient boosting, but there are ways around. One of them is approximate with a smooth ranking objective, and there is another way, which is a pairwise approach, where you make a function of probability that one document is better for this query than another one, and you try to model that probability. You sample these pairs, and you try to model the probability as a sigmoid function of difference of the scores for these documents for the same query, output by MatrixNet. And then when you have this model, you can just maximize the log likelihood of data-given predictions, and that is a complex pairwise objective, but you still can implement that inside gradient boosting. That works really well. Another example is ad-split prediction. So we have search ads, users enter queries, and advertisers enter keywords that correspond to these queries, and we need to match them somehow. We need to show the best ads, and the question is, what are the best ones? So, of course, those are relevant ads which maximize revenue. Maximize revenue is basically this maximize expected money, probability of click multiplied by something like bid in the auction, which is not really what is used because you also need to incorporate relevance to the user, otherwise users will go away. But still you need to predict this P of click, which can be modeled as a binary classification with logos, of course. Just probability of click is sigmoid of the output of your gradient boosted decision trees, and maximize the likelihood again. However, again, here you don't need to compare first ad for first query with second ad for second query. You waste your power on doing correct predictions of probabilities, which you don't need. You only need to rank the ads. If the ranking doesn't change, then your interface to the user doesn't change, so you waste your time. And to avoid wasting model resources on that, you can actually combine classification and ranking objectives, and then train on that with some coefficient. And this is the thing which is really easy to do with MatrixNet. Another problem which we apply MatrixNet in is an external kind of problem, which is not inside Yandex, but helping another company. So we did this with a big local telecom company. So the problem is which telecom users are going to switch to another operator next week. They want to predict that to prevent them from switching actually by giving some offers, discounts, things like that. You don't want to give discounts to everybody, so you want to predict the users with the highest probability of churning. Churn is the event of switching to another operator, and then only giving offers and discounts to those. A week is needed actually to prepare the campaign with all the marketing materials and discounts. And we compared with the telecom's in-house model, basically the same data sets for training, the same for testing. From historical data, we didn't get the historical data before, and I need to mention that this is a problem that they were solving for like decades by this time, because this is the central problem to keep your users. And the metric is a standard industry metric of lifts 10%. How much is the concentration of churners in the top 10%, bigger than the concentration in the general population. So basically we won by 15%, which is a huge leap for a problem which people worked on for decades. On test data, the win was smaller, but that's like an artifact of the fact that between training data and test data in the future, their churn rate for some reason grew 2 times. So we can't really compare models built on one data set and tested on another one, but still that was a commercial pilot, so you have to compare. So, and the amazing fact is that most of this delta was achieved with the first application of MatrixNet without even tuning of parameters, feature engineering, just applying a more sophisticated algorithm to the data. So of course it's not like magic which solves everything, and there are some limitations. So 2 of them is multiple category features. We have like a feature which is not ordered in any way, like region, geography, something like that, or some sparse features like text. And so we have many values, and binarization doesn't really work. So for multiple category features, we use something like bin counting or CTRs. You might have heard about that. For sparse features, a good thing is to stack a linear model inside as a feature, and what we use in production is we have a general framework from MatrixNet accepting features from different feature generators, some of which can be classifiers themselves like a linear model built on just text. Another thing is just cannot divide discretize features. If you want to predict probability of click, you better divide your clicks by your impressions and put it also as a feature inside. And another interesting case is when dependency is really continuous, like a physical dependency, how much materials you put in your steel during steel casting, what will be the output. Or when you have a very good feature, which is an old model, which is already very good, but you want to improve it. So what you can do in this case is also you train a simple model, like linear model in case of continuous dependency, or just baseline model which predicts this one feature, and then train MatrixNet to predict the deltas, basically, in some sense. This is like also pre-built functionality. You can have any baseline and predict deltas based on that, which works much better than training from scratch. So basically the conclusions is MatrixNet is our implementation of grade boosting or decision trees with a lot of bells and whistles, heuristics developed to work well on a wide range of data sets. We applied it both inside Yandex and outside Yandex with a lot of success in comparisons with different teams and different commercial and open source tools. It handles both numeric and categorical features nicely, and almost no tuning is needed, at least for a very good result. You can still do tuning of parameters, but that is like the last mile. And training is parallelized and optimized, as well as application. What we've seen is often superior to other available models. For example, with XGBoost, it's just first, it's much faster, and second, it typically has, even after first application, a few percent quality improvement, and you need to tune parameters with XGBoost. You don't have to do that with MatrixNet, but still you need to understand the underlying algorithm really well to do careful feature preparation, because there are limitations, and knowing them you can do much better. That's all. Thank you.
You said that MatrixNet is also very easy to use. Can you give an example how like a very naive business user would use it?
So we have the standard mode is like you have a file with features already somehow defined, like from database, and there is like tab separated file with columns features, and the last column is a target. And you just run a command MatrixNet minus input and minus output, and then it gives you another file with predictions for that data set, or you can use separate file for, separate file for training, separate for testing. So I mean that is not completely. This case is not completely easy for managers, but for technical managers that's already okay. And also we have inside some web interfaces where you just have this data flow with rectangles, and then you can just input as a input file, upload, and then just run data flow, things like that. So yeah, of course, if you need to do feature engineering, managers usually cannot do that, but typically works with raw data pretty nice. If that's product type, but if that even works better than random or not, is there any signal in the data at all?
Any question?
For the talk, you mentioned for
meta learning several times. Can you elaborate? What kind of meta learning capabilities do you support?
So that was not like capability, that was the approach to developing MatrixNet. So we just gathered data sets from inside and from outside, like search, ranking data set, like prediction rating data set, recommendations for music data set, Netflix data set, and things like that. And then when you change something, like you change leaf regularization function, for example, you just test and compare. If it's uniformly better, then you commit. That's the whole meta learning. Maybe that's the wrong name for it.
Thank you.
What kind of regularization techniques do you use?
So in general, regularization techniques are like, of course, shrinkage. Some of the specialized are like oblivious trees, predefined feature binarization, leaf regularization, where you discount the values in the leaves if there are only a few objects in those leaves, and also we use bagging, of course, with parameter for how much to bootstrap on each iteration. So these are like those standards for really interesting and our own types of regularization. But can't tell you like the exact formulas, but the approaches are those I mentioned and the standard ones.
I'd like to ask you, you said that you use MatrixNet for ranking your search engine. I'd like to ask you, how do you deal with time-aware queries? I mean, such queries where the relevance of the document for them is changing during the time.
Yeah, so there is a whole framework, of course, for search ranking, which consists of different like verticals, like for example, images inside a regular web result page is a separate vertical, and recency is just working as a kind of a separate source. So we train a separate model to predict which queries are going to be hot, and then if the query is hot, we're trying to find documents for those which are recent enough, and then we just blend different sources in the whole web search with another model, which is basically we do first ranking inside each source, and then final re-ranking of those.
Thank you. Any other questions? No? Then thank you very much.